Good afternoon, everyone. I hope you had a great day so far. We are going to spend the next hour or 45 minutes maybe talking about the Loom project. That's the subject of this talk. There are several parts within the Loom project, and we're going to focus on one of them, the first of them, which is the virtual threads. So this talk is about just that, virtual threads added to the JDK as a preview feature as part of the project Loom. I also give you a small hint about what is the structured concurrency at the end of this talk, just for you to have an idea of the big picture of project Loom. All right. So my name is José. I work at Oracle as a Java developer advocate. I tend to publish way too much content on the web. So don't follow all these links. One or two is more than enough. I like to publish also some videos on YouTube, and there is a series of videos called the jconf. Maybe I'll explain one day why I chose this funny name, the jconf. But if you look for the jconf on YouTube directly, it's a hashtag, so you will have all the series that should show up. And there are, I think it's 3 episodes of the jconf about Loom, with live coding, with demos, with explanations about virtual threads, structured concurrency, and also extend local variables. Right. We published with the team at Oracle, with the Java developer relation teams, we published a website called dev.java, along with the release of the JDK 17. JDK 17 has been released a little more than a year ago. So if you're not already on the JDK 17, it means that you are already 1 year late. Who is running the JDK 17? And that's not that many people, 4 of you. JDK 11? That's a good half of you. And JDK 8? All right, so you know that you're running on a version that is almost 10 years old, right? Okay, just wanted to make sure. You know that running on the JDK 8 today is just like when the JDK 8 was running, you were still running on the JDK 4 or 5 or something. Okay, that's the same amount of time there is between both versions. All right, so that's, no, I was kind of joking, okay? But yeah, you should definitely upgrade to a more recent version. That's the dev.java website, and within this website there are community pages. If you are running a user group, you can, and this user group is not referenced on this web page, just send us an email, so because we need to, well, we can add it if you wish to do so. And if you're looking for a user group, for a Java user group where you live, you can definitely check that. And there are also some Java days organized by user group all over the world that are popping up all around the world that you can also follow following this page. Right, and the last resource I would like to show you and talk to you about very briefly is the Inside.java podcast. So if you're interested in very in-depth technical conversations about different aspects of the JVM, well, you can listen to this podcast. It's not really a series of tutorials. It's really more technical and very precise topics that are subject of this podcast. All right. So before we start, just a word of warning. Years ago at Oracle, we used to have safe harbor statements slides. Now we don't have them anymore, so we can do funny stuff instead of that. Okay, so Loom is a preview feature. So it may change before making it as a final feature. Most probably it will change. So just keep that in mind. And that's the same for structured concurrency. Technically speaking, structured concurrency is an incubator API. So it's not really a preview feature, but it's the same kind of thing. If you want to learn all the details about preview feature, you need to connect to this page, which is called the JEP 425 virtual threads, all right, which has been released in the JDK 19. And what I would like to show you really is this effort line, which is an XL effort. Not many JEP are an XL effort. Right, XL means very big. We all agree on that. Yeah. Very large effort. This is the pull request on the code base of the JDK. Sorry, of the JDK. for the implementation of virtual threads, you can see that 104,000 of lines have been changed. The amount of elements changes in the same order of magnitude, so that's really a big thing that has been added to the JDK. Okay, there are actually people who reviewed this pull request. Okay, yes, of course, that's the JDK, so there's some kind of code review at some point. The second JEP is about structured concurrency, so I'm not going to talk much about that, just to give you a few hints. It's also delivered as part of an incubator API this time. It's not a preview feature, but it's the same kind of thing. So you can play with it, definitely. And there's a third JEP, 429, which is extant local variables incubator. That is still, as of today, a candidate JEP. It may make it in the JDK 20. That's next March. Okay, we have one major release of the JDK every 6 months now for a while. So extant local variable may be part of it at that time. Right. If you want to learn more about the Loom project, if you want to provide feedback, if you play with this feature and see bugs or this kind of thing, or think that the API could be improved with this kind of edition, whatever, please connect to this page of the JDK Java.net website. You will find all the elements you need, including the mailing list, and this is where you should submit your comments, bug reports, etc., or ask questions if you want. This is really the right way to go. Great. Before we start, I just would like to start with a small historical view of concurrency in the JDK. Java, when it was released in 1995, was one of the rare languages to integrate a concurrent programming model within the language, baked in the language, and with the relevant API to make it run. All right. So there are basically two objects for that. Well, one interface, runnable. It was before Lambda expression, so to implement a runnable, you would need an instance of an anonymous class. Maybe some of you remember these great days? Oh, 1%, great. I'm not the only one to be old there, right? And the thread class. Okay, the book you had to read at that time is this one. You can still find it. It's a great book, by the way. It's a little dated, of course, because it was published really a long time ago. And the way you could synchronize your code was by using this pattern. We only had one pattern to synchronize code, which is this one. These were the good old days of 1995, Java 1. And then we're jumping to 2004, that's almost 10 years after that, and the release of the JDK 5 and the Java Util Concurrent API. There's a new interface callable to model tasks in concurrent programming. The book you need to read is another one, it's this one. And by the way, it's still the book you need to read if you want to learn about concurrency in Java, because there's no other book than this one, specifically on this topic, which is a bummer. You don't need to create threads on your own, and in fact, it's not the right pattern now to do it. What you're better off with it is to create an executor service. You can submit tasks to this executor service. Your task will be stored in a single waitlist, and when the thread is available, it will pick one task from this waitlist and execute it. And when you do that, you get a future object, and this future object will wrap at some point the result of your task, so you can query this future object with this method. Now, to do synchronization, you have a new pattern, which is this one, the reinterrupt log pattern, okay? So it's not a language pattern anymore, it's an API pattern, right? This is an API. It's not a keyword, synchronized keyword anymore. It works kind of the same, but we're going to see that with virtual threads, there is a difference with the synchronized block. And then you have a bunch of primitive elements, including in a collection framework, to do some concurrency, to have some concurrent structured list maps, etc. And then the next big evolution is between Java 7 and Java 8, right? There is this fork join framework that has been released as part of the JDK 7, which is used in the JDK 8 to implement parallel streams. Maybe some of you have already played with it, all right? And along with it, there is a pool of thread that is created when the JVM is started, called the common fork join pool, which is a pool of thread that will be used by your parallel streams if you are playing with that. which is not, by the way, always a good idea. And the second thing released as part of the JDK 8 is this completable future API. Completion stage is the interface, and completable future is the implementing class, right? That's the subtype of future. And this is where the asynchronous programming model of the JDK is implemented. That's the entry point of this. Maybe some of you have played with the completable future API? Yes? Do you like it? Yes, you do? Wow. Really? Okay. Right. So you see there is some kind of pattern here. 1995, 2004, 2014. It means that every 10 years there is some kind of new things happening in the concurrency programming model of the JDK. And we are in 2022, almost in 2023, and the Loom project is just arriving now. So in fact, we're just in time. Every 10 years, that's now. Okay, that's fine. There is one thing since the very beginning of the JDK that stays the same, and that Loom is going to change, which is once you have given a task to a thread, this task is stuck to the thread. You cannot detach a task from a thread. And there is only 3 possible outcomes. First, the task completes normally, produces a result, and everything's okay. Second, the task completes exceptionally, throws an exception that you can get through your future object. So everything is not okay, but at least it frees your thread. And third, nothing of this is happening. Your task is running forever, and all you can do is just interrupt your thread and kill the task by doing so. Okay? But once you've given a task to a thread, there is no way you can say to the thread, okay, this task is blocking, you should get rid of it, put it somewhere, take another task, and come back to this work later. This is not possible. All right? 2022, 2023, the Loom project is coming. I just show you it's a massive effort, right? And it changes this model. Now we are going to be able to say when a task is blocked, we can remove this task from the thread so that this thread is free to do something else. That's the new thing about virtual threads. Before going to see that, I would like to ask you a question. Why do we need concurrency? Well, if you don't know, that there's a problem, right? Because concurrency is complex. It's hard to get your concurrent code right. When you have a bug in your concurrent system, it's most of the time super hard to detect and to debug, to fix. Race conditions, this kind of thing. Race conditions, we all know about race conditions, right? Oh yes, I see faces like that. Oh, we all know, yes we do. All right, that's really hard to fix, hard to test, hard to make it right. So we'd better have a good reason to use concurrent programming because it will be so much simpler not to use that, right? Well, there are 2 main use cases. The first one is you have some kind of big computation and you have so many cores on your computer that you want to speed up this computation, split this big computation among all the cores you have, okay, with a parallel stream or some kind of other parallel algorithm, and then you will hopefully speed up things. The problems you have when you do that are algorithm problems. Okay, for instance, if you want to sort super simple stuff, you want to sort a big array with millions of elements in it, you are going to split it into small subarrays, sort every subarray, but you're not done once you've done that, because each core has sorted its subarray, which is fine, but then you need to merge all these arrays together, and then you have a merge sort after your quick sorts in parallel. So the problems you have when you do that are algorithm problems. Now Loom is not addressing these kind of use cases at all. Loom is not for that. Okay? Let me say that again. Loom is not for parallel processing. Yeah? Loom is for the other use case, which is, yes, you can see me. Loom is for the other use case, which is basically I/O stuff when you are launching network requests, disk requests, code that is blocking because it's blocking in waiting for some kind of response that is coming from your I/O stack. Okay, that's the use cases Loom is addressing. Great. Suppose you have a Tomcat server and you want to follow the simple model back in the old days of Java EE. Some people are remembering the old days of Java EE? Yes? No, 1%. Wow. I didn't know that was so old. Okay. The idea is that you have one request per HTTP client. Or you're doing some database access and you have one transaction per thread. Okay? How many threads do you need to keep your CPU busy? I'm not talking about, oh, I have 10,000 clients, 100,000 clients. No, I have a CPU and I want the CPU 90% busy with this kind of model. Well, it's quite easy to check, in fact. Preparing the request that's in memory computing. Okay, you need to set up the string of character, your certificates, your blah, blah, blah. This is all string of character HTTP, right? Most of it. So you can do that in memory. And preparing the request, the time scale of this kind of computation is in the order of 10 nanoseconds. Okay? And then you make your query, you launch your request, you go to the network, and now you wait for the response. Another time scale is 10 milliseconds. That is 1 million times longer. And then you get your answer, your response. You have some kind of JSON or XML or whatever in it, HTML maybe. Okay, you need to process that, and it's again in the order of 10 nanoseconds. So if you just draw this sketch in that way, nanoseconds, milliseconds, nanoseconds. Okay? If you do that for one thread, then your CPU is idle 99.9999, there are 4 nines there, % of the time. So you bought this shiny Core i, blah, 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 last version, whatever, with plenty of cache, blah, 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 and you are not doing anything with it, basically. Okay? In fact, this sketch is not at the right scale because the green part is less than a pixel. It's 1/1000th of a pixel. Okay? If you have about 2,000 pixels on the screen, that's the order of magnitude. So basically, you're not doing nothing. So if you want a CPU that is busy 90% of the time, let's say 100% of the time, then you need 1 million threads. Plain and simple. 1 million threads. Well, can you afford to have 1 million threads on your machine? If you can, then there's no problem. Well, the problem is the following. It takes about 1 millisecond to launch a thread. So launching 1 million thread, that's about 20 minutes. Okay? 1,000 seconds, that's about 20 minutes. And every thread, every platform thread in the JDK consumes about 2 megabytes on a stack. Meaning that if you want 1 million of them, then you have a 2 terabytes machine. Well, that's not a cheap machine. Definitely not a cheap machine. And if you want to do some context switching, it's even worse. So in a nutshell, having 1 million threads on a machine is possible as long as you have a very high-end machine. And even if you are, it takes so much time to launch them, then you'll probably be needing another model. So what are the solutions so far? Well, the solutions are asynchronous programming, okay, with completion stage, completable future, and all the solutions that you have there. They lead to code that is hard to read. I don't know what is the hardest between reading and writing such code, to be honest, but both are hard, right? It's hard to debug. Going step by step in such a code is just a nightmare. You never know where to put your breakpoints, etc. Writing unit tests for this kind of code, and I'm going to show you some kind of code like that in a minute, okay? Writing unit tests for this kind of code is next to impossible. And when I say hard to profile, it's in fact impossible to profile. So this kind of solution is working. Can't say it's not working because everybody uses them, okay? But it's definitely not, I'll say, maybe it's possible to do better than that. That's the idea. So that's precisely what Loom aims to address, to fix this kind of problem. Loom introduces the notion of virtual thread. Now, what is a thread? A thread is this kind of thing. That could almost be Java 1 code. It's Java 1 code plus Lambda expressions, okay? But that's it, that is a, you know what, do you prefer to see slides or to see IDEs, like, I mean real code? Okay, I don't want to know, I'm going to show you real code. Whatever you think about it, I think real code is so much better to see this kind of thing. Okay, I have this code here. I'm going to present that in that way. Is it big enough? Yeah? Great. So that's basically a platform thread. And if I run it, well, this is something that you can see. I'm running the JDK 19, and I just enabled the preview features so that we can, well, use the preview features precisely. There's no real trick there. First of all, well, this is really Java 1 code. You shouldn't be launching threads like that starting with Java 4, that is 2005, sorry, Java 5, 2004, okay? You really should be using an executor service. But now what you can do is use the factory method of platform thread, and you see that I also have of virtual. And then you have either a started method or an unstarted method. And you can pass a runnable to it. So I'm going to pass this task to it. And this is, I would say, the new pattern to create threads using Loom. And it does exactly the same thing. The nice thing here is that you do not expose the real class of the thread anymore, right? This is a P thread, but I should really put a var there. And now my class is invisible. And if I just copy paste this pattern and replace this, so this is going to be a V thread. Okay, because it's a virtual thread now that I'm going to create. V thread, and here I'm just going to call of virtual, and this is going to give me a virtual thread. All right, this virtual thread is a thread, a plain old thread. The class is different. The class is virtual thread. It's not a public class, so you cannot play with it directly, but it's in the JDK. You can definitely check it if you want. And this virtual thread class is an extension of the thread class itself. So wherever you use a regular thread, you can just replace that with this pattern, and it will work just fine. If I launch this virtual thread, you see that there's something more that is happening here. Okay, that's my thread, number 23. The JVM already launched 22 threads for itself. There is the JIT, there is the garbage collector, there are many things that are running in the background. And here, my virtual thread is there, but it's running on top of another thread. This one, taken from a fork join pool 1, thread 1, okay, that is itself a platform thread. So in fact, a virtual thread is something that is running on top of a regular platform thread, which is called the carrier thread. Okay? So you're going to tell me, okay, but we didn't do much here, because before we were launching directly a platform thread, and now we are also using a platform thread, so what's the deal? Well, precisely. I'm going to show you something else. Where are you? Oh, sorry. Okay, I don't need you. I'm going to show you another example. Here I'm going to create a list of threads, of virtual threads. Because I like stream, I'm going to create an in stream from, let's say, 0 to 10. Okay, and I'm going to change this index. This is going to be a map to obj. Yeah. I'm going to take the index, and with this index, I'm going to create a virtual thread there. Okay, and this task there, sorry, I should have created this task beforehand. It's just going to print system out. You know what? It's the same task as here, so I'm just going to take you there, copy this, put you here, okay, and do this. But I'm not going to do that for all the threads. What we're doing? Okay, I'm not going to do that for all the threads. I'm going to say, okay, if the index is equal to 0, then I'm going to print this task, and after that, sorry. That's my runnable. And I want to return this. Let me get rid of this. Okay, so this is the virtual thread I'm creating. Okay, and if, so sorry, I'm just messing with the stuff. Okay, that's the one. This is what I want to do. Map to obj, and I want to return U. And I'm going to put that in a list. I've got a toList method on the stream API, which is really great. And the task I'm going to make is the following. Sorry. I already have this index there. Oh, shit. This code was compiling just a minute ago, right? And now it's not compiling anymore. It's not compiling because this should be a runnable, and it's not a runnable anymore for some reason. Okay, so that's my task. Okay, and I'm going to change it in that way, in that if the index is equal to 0, then I want to display that, the name of the thread. So I'm only interested in the first thread that I'm going to create. All right, and after that, I'm going to go to sleep for like, no, sorry, thread.sleep for like 20 milliseconds. 20 milliseconds will be enough. So basically what I'm doing here, I need to try catch this thread.sleep. So basically what I'm doing here is that I'm just telling, okay, for 20 milliseconds, we are not going to do anything, and that's roughly the time it takes to make some kind of network request. So I'm blocking this thread for 20 milliseconds. All right? And once I'm done, and I'm doing that only for the first thread, I'm going to display this virtual thread again, and I'm going to copy this. So 1 time, 2, 3, 4 times. So I'm doing that 4 times. I'm printing the thread, I block it, print it again, block it again, print it again, block it again, etc. All right? And I'm launching 10 threads, and I'm just displaying that for the thread 0. And after that, I just start the thread and join them. So let me run this code. And you see something really weird happening. What is red on this console? Can you see it? Well, it's always the same virtual thread that I'm looking at, number 23, okay, because I already have 22 threads running on the JVM. But the platform thread that is used by this virtual thread is never the same. It's the first, number 1, number 7 again, number 8, and number 5. So it means that the virtual thread jumped from one platform thread to the other when I blocked it. I blocked it, it went somewhere, it came back, but not on the same platform thread. It means that this task has been in fact run by 1, 7, 8, 5, 4 different platform threads. And it's the same task. Okay? This task is this stuff. It's all this code. Well, this is new. Never saw that before, unless you already played with virtual threads. What is happening in this sleep method that is here? We're going to visit it. I am in the thread class, and you see that I have 2 different parts in this sleep method. Am I an instance of virtual thread, or am I just a regular thread? That's the rest of the code. If this is a regular platform thread, then it calls in the end sleep 0. This is some JFR code for those of you who are playing with the Java flight recorder. Okay. In the end, it's called sleep0, and sleep0 is just a native method written in C, the method that we've been executed for years. And in the virtual thread part, it's calling sleep nano. Let me visit that. Do sleep nano here. You see, this is some JFR code again that is calling do sleep nanos. So let me go there. And then I have a park nano there. Let me go in there. Yeah. And then there is this yield continuation. I'm still just jumping from the right place of the code that I want to show you. And here I'm still in the virtual thread class. Here I have this yield continuation. And at some point, there is this object called continuation that is calling its yield method. And this is where all the magic is happening. Okay? Let me just run another example, with this continuation object. Now, this continuation object, you cannot play with it in your code because it's in a package called JDK internal VM. So it should really be called don't touch me. Okay, JDK internal, don't touch me, don't look at that, right? But you can still play with it just for experimentation purposes. I'm going to try to run this code. It may not run because, yeah, you see illegal access error, yeah, machin, you cannot call me, cannot access class, blah, blah, blah. So when you have that, you just copy paste this piece of stuff. You just go there, open the options, paste it here, apply, okay, run again, and then everything is fine. You just need to tell the JVM that yes, you're a nice person and you can run this stuff. So what is this continuation doing? This continuation is just taking another runnable here that is just displaying C1 thread current thread, and that's it. And here I'm just launching this continuation just as if it was a thread. I'm just calling run, and it basically runs the runnable that I have in it. Okay? So now I'm just going to do that. I'm going to say, okay, let's continue. I'm going to call continuation.yield. This guy needs a scope object, so I created a scope object there. We don't really need it. And I'm going to copy this again and paste it there for C2. All right? So now I have this continuation. I'm displaying that. I call yield, okay, on the run, and then I just display continued in the main method. I'm going to run that. And you see that what has been displayed is just start, this message. Then run has been called, and it just executed this piece of code until I called yield there, and then carried on with the main code that is here. Okay? So it's just like you have some kind of return in the middle of a method, but with still some code after that. Because I still have some code after this yield that has not been executed. Now if I run the continuation again, what is going to happen? I'm going to display last message there, and run that. And now what you can see is very unexpected. You've never saw that in Java before, right? Start has been displayed, and then the first part of the continuation until the yield. Then yield exited the task that this continuation was executing. Okay, and then we displayed continue. And if you call run again, it continues to run the task of this continuation where it was before. Okay, so it's more than a return because you call the same method twice and it just executes the first part of the method, yield, and then executes the second part of the method if you call run again. You see that? And that's exactly what is happening with this thread.sleep. You execute the first part of the task, thread.sleep, that blocks the task. Internally, it calls continuation.yield. And when the timer is done, when you've waited for 20 milliseconds, then there is a signal continuation.run, and then it continues to run the rest of the code after the sleep. But in the meantime, the platform thread is free, okay? The code of your task is not on a platform thread anymore. I've got some slides to show you what's really happening. Let me show you. You see, you have the full stack of your platform thread, and in the stack there is a part that is dedicated to the platform thread, we don't touch that, and then there is your virtual thread on top of that. If you call continuation.yield, then all the part of the stack that is specific to this virtual thread is going to be copied in a heap memory. It makes this platform thread free to execute other tasks. And when this task that it was waiting, that was blocked on some synchronization, waiting for some code, sleeping, whatever, when there is a signal telling, hey, now you can execute this stuff again, then this heap is sent back to the platform thread, and the first platform thread that is available is going to execute it again, calling continuation.run. Okay? So this yield stuff will copy the stack to the heap memory. So now the situation is this one. Yes, question? Oh, you need to shout much louder than that. Sorry for that.
How is this different from Java futures or Java completable futures?
It doesn't have anything to do with Java futures and uncompletable future. Futures are not doing that at all. The future, the stack is on a platform thread. If you have a blocking call on it, then the platform thread is blocked until the blocking code is done. And that's it. Now, if your code is blocking, this is happening. You take the task, the stack of your virtual thread, you remove it from the platform thread, put it in a heap memory, and now this platform thread is free to execute something else. Your platform thread is never blocked. Your virtual thread is blocked, not the platform thread. Okay? At some point, this stack will be sent back to this fork join pool because all these platform threads are in a fork join pool. So this stack is going to be sent back to this fork join pool, and the first thread that is available will execute it. It may be the same thread as the first one, but it may be a different thread also. And this is what we saw. Well, this is what you saw, by the way. If I run this code again, that's the code that showed you the jumping threads. You will see that if I run it several times, the different threads will never be the same. Okay? Now the question I would like to ask now is how many, oops, sorry. Is how many platform threads do you need to launch your virtual thread? So now I have basically the same code as the previous one. The difference is that it's not going to display anything because there will be too much information. And I have two ugly regular expressions there to analyze the full name of the virtual thread and to extract which platform thread is running this virtual thread. Okay? And you see that if I'm running 10 virtual threads, then I have 12 cores on this laptop. I need 7 workers, so 7 platform threads for 10 virtual threads, which is a lot, by the way. Let me run that again. Okay, 7, fair enough. If I put 100 virtual threads, that's 8. What about if I put 10,000? Well, that's 9. 100,000? That's still 9 platform threads. What about I try to launch 1 million threads? Because that was the goal in the first place, remember? Have you ever tried to launch a million platform threads? You never. Yes, you did. But in fact, it crashed your laptop, right? Yes, this is what happened. Did I launch that? I didn't. Let me click here. So 1 million virtual threads. Still 9 platform threads. Okay? They are not doing much, but still, I have 12 calls, it means that I still have 3 calls available to do something else, right? Like GC, just-in-time compiler, whatever. And it took 3 seconds to create this million virtual threads and do the stuff. Not that bad. 1 million. This, you cannot do that with regular platform thread. It's just not possible. Okay. Now, there's something I would like to show you, which is the following. Now, I have this basically the same code as the previous one, okay? Still my 100 virtual thread that I'm launching, but now what I'm doing is incrementing a counter in a synchronized block. I'm not sleeping again, so I'm still blocking my virtual threads, but in another way, because synchronization is a way to block virtual threads. And what is going to happen? Sorry, I'm not launching the right code. Okay. I need to renew. Well, sounds like this thread jumping that we saw on the previous example is not working anymore. Is it? Not really. There is a condition that must be fulfilled for a virtual thread to be able to be copied in a heap memory and go back and be executed on another platform thread. And this condition is the following. I don't know if some of you have played with the C language. Yeah? You know the C language? Well, everybody heard about it. But in C, when you have a function, and when you have a variable defined within that function, you can get an address on that function. You can write int I equals 0, and then int p equals the address of I, which is the ampersand symbol followed by I. And that's the address of the I variable. Now this variable is an address on the stack, not on the heap. So using C, you can get the physical address on the stack of a variable. What do you think is going to happen if you have a stack with this kind of stuff in it, and you move the stack somewhere else, and you put it back where it was? Almost. There's very little chance that this address you had on the stack is still valid. It's still the right address where you had this variable. And the problem is that in Java, you can call some C code. And some C code can call some Java code back. So Loom is able to detect that. And if on the stack of this virtual thread, Loom detects that there are some C code in it, it will prevent this movement from the stack to the heap of this virtual thread. So it pins this virtual thread on a platform thread, and this virtual thread will not be able to jump from one platform thread to the other. So if you block this virtual thread that is pinned, now it's also blocking the platform threads. Now, there are several strategies to get rid of that, but you still can block a platform thread even with Loom if you have some C calls, among other things, in this virtual thread. And this is what's happening here. The synchronized block doesn't really call some C code, but it has an array to store the threads that are waiting to enter the block of code that is protected by the synchronized keyword. And this stuff is written is an array, and it has an address on the stack. So if you have some synchronization block or some addresses on the stack within your virtual thread, then this virtual thread will be pinned on the platform thread. If this virtual thread is not blocking, or blocking for a very short amount of time, like several nanoseconds, it's not too bad. And you will not see any kind of overhead or performance hit because of that. But unfortunately, if your virtual thread is doing some kind of I/O that is long blocking, then you will have a performance hit. So you just need to be aware of that. By the way, if you want to fix that, you can just use synchronized blocks. Okay? In that way, here I just replaced the synchronized blocks with a lock, reentrant lock, and try lock and unlock, lock and unlock. And if I run this code, in that way, so this code is basically doing the same kind of thing, but with a different pattern of code. It's not built on synchronization, classical synchronization, but the use of reentrant lock. And now you can see that the virtual thread is jumping from one one platform thread to the other again. So the problem of pinning this virtual thread on a platform thread is fixed. Okay? Great. Let me go back to the slides. So there are just a few things I would like to tell you to wrap up this presentation of virtual thread. First, you already know that, but a platform thread is in fact a wrapper on an OS thread. That is a heavyweight object, an expensive object both to create and to block. A virtual thread is not tied to any platform thread and not tied to any operating system thread. It's a free object. Okay? A virtual thread is installed on a platform thread only if it's doing some computations. That is, when it's blocked, it's not blocking its platform thread, it's moved to the heap. The price of blocking a virtual thread is now just moving its stack from the heap back and forth, which is of course much, much cheaper than blocking a platform thread. Creating a virtual thread is cheap. It means that blocking a virtual thread is also cheap. So now you can ask yourself the question, is it really worth pooling virtual threads? Do you pool resources that are just cheap to create, to block, to kill, whatever? Well, the answer is no. Don't do that. It's useless. And the JVM doesn't do that, by the way, neither the API. Loom is not implemented by the JVM. All right? There are two things that are really written in the JVM. It's this copy of the heap memory back and forth, sorry, the stack back and forth from a heap, okay? And there are also modifications to the garbage collection that have been added, because now you can have references, because you have portions of stacks in the heap, the garbage collectors need to check that in order to work properly. And that's it, okay? So these are the only two portions of code that have been written in C, but all the rest is just Java APIs. All right. I'm not sure at what time I should be ending this talk. Do I still have time? Sorry? 4:40. Oh, great. I have 10 minutes. More than enough. Absolutely fantastic. So I have a little time to talk to you about structured concurrency. This is going to be very, very fast. I'm not going to show you some demos. If you want to see some demos of structured concurrency, you can check my YouTube channel, the Java YouTube channel, the Jeb Cafe. I did all that several times already. So basically, I would like to show you a use case, which is this one. You want to create a travel page, okay, and you need to query two servers to create your travel page, a server for quotation and a server for the weather forecast. And you want to do that asynchronously. Super easy to do with completable futures, any kind of asynchronous API that you may have, right? And basically, the code you need to write is the following, which is super easy to read. Yes? Oh, not so sure. Super easy to write? No? Super easy to unit test? No? But why are you writing such code? My God, we must be all mad to write such ugly code. And what about debugging step by step? Yes, it's a disaster also. Yes, we all agree on that. Okay, and you know what? This code doesn't even do exactly what you want to do, because what you really want to do is query more than one quotation server to get the best quotation for your travel, and also more than one weather forecast servers to get the first one that is going to answer. Okay, now you need to modify this code to do that. Good luck. What is complex in this code? Well, everything. But there's one thing that makes it really complex, is that when you're looking at a specific portion of code, you never know what thread is going to execute your lambda expression. It's full of lambdas, callback within callback within callback within callbacks. Okay? And in the end, you don't know who is going to execute your lambda. And that creates some kind of fog in your code that makes it super hard to understand. You can write this code in that way using the structured concurrency. You have a scope object that you can easily extend. When you want to launch your asynchronous task, it's just fork, 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 fork. Okay, so that's the 3 tasks. All right, and then when you're done, you call join. Join will return when your tasks are done. Quite easy to understand. And then get first weather, we are going to take a look at this method. See how it's written, it's really super easy to write. That's basically how you use a structured task scope object. No callback. It's all executed in the same thread. If you want to go step by step, you can do it. I'm not sure if it's super useful to do that, but it's very easy to do. Writing a unit test for that, super easy. Why? Because this code is written in an imperative style and it's monothread. Everything is executed in the same thread. So that's for the weather forecast. Same for the quotation. Exact same pattern. Well, I like that because I have only one pattern to learn. Much easier to have to learn like 10 or 15 patterns, right? It's exactly the same. And we're going to see what was the first? Yeah, get first weather. Guess best quotation, I'm going to show you that method. Okay? And once you have that, you just wrap these 2 scopes, method call, okay? You have a return best quotation. I had a return first weather in the first place. So you put that in methods and you just need to call them asynchronously to build your travel page. And once again, it's the same code. Same scope. No, it's not the same scope. You need to create the scope. It's so easy that it's just funny. All right? Fork, join, get the result, and that's it. Okay? And this is why it's created a structured task scope, because one scope launch another scope, that launch another scope, etc., etc. The problem with having a million threads is that if you don't put some kind of structure on them, then you're done, you're lost. You cannot handle them. I don't know if you're using IntelliJ or Eclipse, but there is a panel in Eclipse and IntelliJ where you can display all the threads of your JVM. I'm not even sure this panel can support 1 million elements in it. But if you have 1 million elements in it and you're looking just for one specific thread, good luck scrolling. I'm not even sure that the wheel of your mouse would support that. Okay, so I told you that I was going to show you the inside of the scope object. Basically, you have one method to override, which is called handle complete. And handle complete is a callback on the future that is going to be created once the task you submitted is done. Okay, so if you submit 3 tasks, this handle complete method will be called 3 times. But at each time, it only handles one future at a time. All right, imperative code. You want to debug that in step by step, super easy. You want to write a unit test, super easy. And if you read it, well, I guess you just understand it. Future, 4 states, running, success, failed, and canceled. That's it. Okay? Best quotation, I told you I was, so this task is going to be called, that's for the quotation, yes? That's for the quotation. So this task is going to be called like 3 or 4 times for each server you are going to query. All right, and you see that on the line success, you put the result of the future in a collection. So at the end of the day, when the join method has returned, all the futures are done, all your tasks have completed successfully. All right, so you just need to call the best quotation method, but once again, this best quotation is just imperative programming, executed in a single thread, super easy to understand, super easy to write. Writing a unit test for that, it's really super easy also. And if you want to go step by step in that, it's just a simple stream, so there's no problem with that. Okay? And by the way, if you really want to handle exceptions, that's the method to handle the exceptions. That's Java 7 code. Well, no, Java 8 because there is a for each method. Okay? So that's the gist. That's the kind of pattern you can write. Let me show you the completable future pattern again. Which one do you prefer? Yeah, okay. Great. So let me just wrap that. Loom allows you to launch 1 million thread on the JVM. I could have go up to 10 millions, in fact. It's not really a problem. I just stopped at 10 million because that was enough. But if you want to launch 10 million, it's also working quite easily. Okay. Now the problem is, well, what are you going to do with this million threads? Not to deal with million. Hey, I was not used to that. Okay, so there's another way of writing your asynchronous code, which is called structured concurrency, but which is entirely based on virtual threads. Every asynchronous task is in fact executed in a virtual thread, and if this virtual thread blocks, it doesn't matter. I mean, blocking a virtual thread is just okay. You don't need to write non-blocking code again anymore. Okay? And this is what I wanted to talk to you about Loom today. So thank you very much. I don't know if you have questions. Maybe some of you have questions? You don't have any questions, so it means that everything is great. Yeah? We agree on that?
Now we'll play with it.
Now you need to play with it. Download the JDK 19, activate the preview feature, check my GitHub account. All the code that I showed you, including the structured concurrency one, is on my GitHub account, so you can just grab it, download it, and play with it. And if you have problems, well, there's a Twitter to chat about that. I will gladly answer your question. Thank you all. Thank you very much.